A DDoS attack can overwhelm an application, disrupt availability, and cause significant financial and reputational damage. And the challenge isn't just blocking one suspicious IP address. Modern attacks can generate enormous amounts of traffic from thousands of systems at the same time. Today, we're going to build multiple layers of Azure network defense. We'll use Azure DDoS protection to defend public-facing resources, Azure Firewall to inspect and control traffic, and routing to make sure the traffic we care about actually passes through our security controls. This is Hired in IT, where we turn IT beginners into professionals. Let's build real network defense. Last time, we shielded HTTP applications with Application Gateway and Front Door, Layer 7 protection, Web Application Firewall, and global routing. Today, we're moving down the stack to defend against volumetric attacks and control how traffic moves through our Azure networks. By the end of this video, you'll walk away with 3 concrete tools: DDoS network protection for eligible public-facing resources in protected virtual networks, Azure Firewall for centralized network and application traffic control, and a hub-spoke inspection design using user-defined routes, or UDRs, or virtual WAN routing, intent to deliberately steer traffic through your security layer. Let's break them down. DDoS attacks generally fall into 3 major categories. Volumetric attacks attempt to consume available bandwidth. Protocol attacks attempt to exhaust network or infrastructure resources. And application layer attacks target services such as HTTP and HTTPS. Azure DDoS protection focuses primarily on Layer 3 and Layer 4 attacks, detecting malicious traffic patterns and applying mitigation at Microsoft's network edge. For Layer 7 web attacks, you add a web application firewall on services such as Azure Application Gateway or Azure Front Door. Together, DDoS protection and WAF provide layered defenses against both network layer and application layer attacks. Quick checkpoint. What are the 3 major categories of DDoS attacks? Volumetric attacks attempt to consume available bandwidth. Protocol attacks attempt to exhaust network or infrastructure resources. And application layer attacks target services such as HTTP and HTTPS. Azure DDoS protection primarily focuses on Layer 3 and Layer 4 attacks, while Web Application Firewall helps protect web applications at Layer 7. Remember that distinction. We're going to build both layers into our architecture. Azure provides multiple levels of DDoS protection, and understanding the difference is important. First is Azure's built-in infrastructure-level DDoS protection. This protection is automatically included with the Azure platform and helps protect Azure's infrastructure against large-scale network attacks. Next is DDoS IP protection. IP protection lets you apply enhanced DDoS protection to individual supported public IP resources. It's useful when you only have a small number of public-facing resources that require advanced protection. Then there's DDoS network protection. Network protection is designed for broader environments where you want to protect eligible resources associated with protected virtual networks. IP protection and network protection share core DDoS detection and mitigation capabilities, but network protection adds important enterprise benefits such as DDoS rapid response support, cost protection benefits for qualifying attacks, and potential web application firewall pricing benefits. So remember, infrastructure protection is built in. IP protection targets individual eligible public IP resources. Network protection provides broader protection for eligible resources associated with protected VNets, plus additional enterprise capabilities. So what do you gain when you move to DDoS network protection? First, adaptive traffic profiling helps Azure understand the normal traffic patterns of protected resources so mitigation can respond to abnormal attacks. Second, you get enhanced monitoring, metrics, alerts, and attack analytics through Azure Monitor. Third, eligible customers gain access to Microsoft's DDoS rapid response team during serious incidents. Fourth, there's cost protection. But be precise about what that means. It doesn't mean every resource charge created during an attack simply disappears. For qualifying documented DDoS attacks, eligible customers may receive service credits for certain DDoS-related scale-out and data transfer costs, according to Microsoft's current cost protection policy. And finally, DDoS network protection complements Web Application Firewall. WAF remains a separate Layer 7 security service, but eligible network protection customers may receive pricing benefits when using supported Azure WAF services. That's defense in depth, not one product trying to solve every problem. Now let's see what deployment looks like. First, create an Azure DDoS network protection plan in the resource group and region required by your architecture. Next, associate the protection plan with an eligible virtual network. Once the VNet is protected, supported public IP resources associated with that network can benefit from DDoS network protection capabilities. On screen, I'll show both Azure CLI commands. First, the command that creates the protection plan. Then, the command that associates the plan with our VNet. After deployment, we'll verify the association from the Azure portal, rather than simply assuming the configuration succeeded. That's an important production habit. Deploy, verify, then monitor. In the Azure portal, associating DDoS network protection with a virtual network takes only a few steps. Open your DDoS protection plan, go to Protected Resources, select Add, and choose an eligible virtual network you want to protect. You can also enable protection directly from the VNet's DDoS protection settings. There's no VM reboot or application outage required. Once protection is enabled, Azure begins establishing traffic baselines so mitigation can adapt to the normal traffic patterns of protected public IP resources. One DDoS protection plan can protect multiple eligible VNets, making centralized protection practical for environments with many applications. Just remember that DDoS protection plans and protected VNets have Azure subscription and regional requirements, so always validate your architecture against the current Microsoft documentation before deploying at scale. Before we move to Azure Firewall, quick checkpoint. Does DDoS network protection replace a web application firewall? No. DDoS protection primarily helps defend against network layer volumetric and protocol attacks. WAF protects HTTP and HTTPS applications against Layer 7 attacks such as SQL injection and cross-site scripting. And neither one replaces network access controls such as NSGs or Azure Firewall. That's the foundation of defense in depth. Different controls protect different layers. You've protected your network against large-scale DDoS attacks. But DDoS protection doesn't replace good network access control. Imagine a developer creates a test VM and temporarily allows RDP on TCP port 3389 from the internet. The rule is supposed to exist for an hour, but nobody removes it. Automated scanners discover exposed services constantly, and that VM can quickly become a target for password attacks. A properly configured network security group could prevent this by restricting RDP to trusted source addresses or blocking internet access completely. but NSGs primarily provide Layer 3 and Layer 4 filtering. They don't replace the centralized application filtering, threat intelligence capabilities, logging, and advanced inspection available with Azure Firewall. That's why enterprise network security isn't NSG versus firewall. It's NSGs and Azure Firewall working together as layers of defense. Network security groups are essential but limited. They check source IP, port, and protocol and remember return traffic automatically. What they can't do is look inside the packet, filter by domain name, or tap into Microsoft's threat intelligence. That's where Azure Firewall steps in. A fully managed service that brings deep application awareness and blocks known bad IPs in near real time. Azure Firewall is a fully managed firewall as a service. It sits between your workloads and the world, inspecting traffic in both directions, east-west across VMs and north-south to the internet or back to on-premises. Because Microsoft handles the scaling and high availability, you apply a policy, not a server. It logs every allowed and denied connection, and it integrates threat intelligence to automatically stop known malicious traffic. Azure Firewall comes in multiple tiers, and choosing the right one depends on how deeply you need to inspect traffic. Azure Firewall Standard provides the core enterprise firewall capabilities, stateful network rules, application rules using FQDNs, DNAT, and SNAT, threat intelligence filtering, DNS capabilities, and centralized policy management. Azure Firewall Premium builds on those capabilities for environments requiring deeper inspection. Premium adds advanced security features such as TLS inspection, intrusion detection and prevention, IDPS, and additional URL and web category filtering capabilities. Here's the simple way to remember it. Standard asks, should this connection be allowed? Premium can go deeper and ask, what is actually happening inside this connection? For regulated, high security, or zero trust environments where encrypted traffic inspection and intrusion prevention matter, Premium becomes much more compelling. Azure Firewall capabilities continue to evolve, so validate the exact tier features against Microsoft's current documentation when designing a production architecture. A classic hub-spoke design places Azure Firewall in the dedicated Azure Firewall subnet, which should be sized appropriately for Azure Firewall deployment and scaling. If you're using Azure Firewall's formal forced tunneling configuration that requires the management interface, you'll also use a dedicated Azure Firewall Management subnet. Your workload, VNets, connect to the hub through VNet peering. But here's an important point. Peering alone does not force traffic through Azure Firewall. With appropriate user-defined routes, peering settings, forwarding configuration, and valid return paths, spokes can send selected east-west and north-south traffic through Azure Firewall for centralized inspection. That's what makes the hub-spoke model powerful. The firewall provides a security policy. Routing determines which traffic actually reaches it. Quick recall. Which dedicated subnet holds Azure Firewall and how large should it be? Answer: Azure Firewall Subnet. For current Azure Firewall deployments, plan for at least a 26 subnet. The dedicated subnet gives Azure Firewall the address space it needs for deployment and scaling. And remember, the subnet name must be exactly Azure Firewall Subnet. Now let's deploy Azure Firewall into our hub network. The firewall uses the dedicated Azure Firewall subnet that we created earlier. Once Azure Firewall is deployed, Azure assigns the firewall its private IP configuration. That private IP becomes extremely important because workload route tables can use it as the next hop when we want traffic inspected by the firewall. On screen, I'll show the deployment commands and then retrieve the firewall's private IP address. There's also an important distinction to remember. If you configure the specific Azure firewall feature called forced tunneling, the firewall requires its dedicated management configuration and Azure Firewall Management Subnet. That's different from simply creating a workload UDR that sends internet-bound traffic to Azure Firewall. We'll separate those concepts clearly in the next section. Quick checkpoint. When do you need the additional Azure Firewall Management Subnet? Answer: when you're using Azure Firewall's formal forced tunneling configuration that requires the dedicated management interface. The Azure Firewall Management Subnet supports the firewall's management traffic and platform operations separately from the data path. That's an important distinction. A workload UDR sending 0.0.0.0/0 to Azure Firewall does not by itself mean you're using the Azure Firewall feature called forced tunneling. Sometimes workloads need outbound access to services such as Windows Update, Microsoft services, or other internet applications. Trying to maintain large lists of destination IP addresses can become difficult because cloud service addresses can change. Azure Firewall application rules allow you to control supported outbound traffic using fully qualified domain names, or FQDNs. For HTTP and HTTPS traffic, Azure Firewall can use information such as the HTTP host header and TLS server name indication to evaluate the destination. Instead of creating broad wildcard rules, use the relevant FQDNs, or supported FQDN tags, for the service you're allowing whenever they're available. For example, Azure Firewall provides FQDN tags for certain Microsoft services that can simplify rule management. The goal is not allow anything Microsoft. The goal is allow the specific services this workload actually requires. That's least privilege applied to outbound network access. Azure Firewall can subscribe to Microsoft's threat intelligence feeds, a constantly updated list of millions of known malicious IPs and domains. When you enable threat intelligence, the firewall automatically matches traffic against this feed. Start in alert-only mode for a week to monitor. The firewall logs every match without blocking, so you can verify no legitimate traffic is flagged. When you're confident, flip the switch to deny. The firewall then instantly blocks command and control servers, botnets, and phishing sites with no manual block list to maintain. That's one-click blocking of known bad actors. Imagine a finance VM needs outbound internet access. You deployed Azure Firewall in the hub, so you assume its traffic is protected. But there's a problem. The VM's outbound traffic follows another route and never reaches the firewall. The firewall can't inspect packets it never sees. That's why routing matters. For a workload subnet, you can create a user-defined route for 0.0.0.0/0 and set Azure Firewall's private IP as the virtual appliance next hop. Now traffic matching that route is steered from the workload subnet toward Azure Firewall before reaching the internet. The firewall can then evaluate the connection against your network rules, application rules, and threat intelligence configuration. If the destination is identified as malicious and your policy is configured to deny it, the firewall can block the connection. Here's the important terminology. This is workload traffic steering, or routing workload egress through Azure Firewall. Do not confuse it with the Azure Firewall feature, officially called forced tunneling. That's a different configuration. Let's build the user-defined route that steers workload internet traffic through Azure Firewall. First, create a route table for the workload subnet. Next, add a route with the address prefix 0.0.0.0/0. Set the next hop type to virtual appliance. Then specify Azure Firewall's private IP address as the next hop. Finally, associate that route table with the workload subnet. On screen, I'll show the actual Azure CLI commands for each step. Once the route is associated, traffic matching 0.0.0.0/0 is directed toward Azure Firewall. But here's an important architecture lesson. Do not automatically disable BGP route propagation just because you're using Azure Firewall. Whether BGP propagation should remain enabled depends on your VPN, express route, virtual WAN, and hybrid routing requirements. After making your routing change, inspect the subnet's effective routes and verify that Azure is selecting the path you intended. Remember the terminology. This UDR steers workload egress through Azure Firewall. Azure Firewall forced tunneling is a separate feature used when the firewall's own internet-bound traffic must be directed toward another next hop, such as an on-premises security device or another network virtual appliance. Quick checkpoint. You created a 0.0.0.0/0 route on a workload subnet with Azure Firewall as the next hop. What should you verify before assuming the design is secure? Answer: check the subnet's effective routes and confirm that the traffic you intend to inspect actually uses Azure Firewall as its next hop. If you're connected to on-premises networks through VPN or express route, examine those learned and propagated routes as well. Then verify that the traffic reaches Azure Firewall by reviewing firewall logs or using Azure network troubleshooting tools. Remember, deploying a firewall doesn't guarantee inspection. Routing determines the actual traffic path. Before we continue, let's clear up something that causes confusion. NAT Gateway and Azure Firewall can both be involved with outbound connectivity, but they solve very different problems. NAT Gateway provides scalable outbound internet connectivity and source network address translation, or SNAT. It's excellent when workloads need predictable outbound public IP addresses and high-scale internet connectivity. But NAT Gateway isn't a security inspection firewall. Azure Firewall provides centralized network and application filtering, threat intelligence capabilities, logging, and, depending on the tier, advanced inspection such as TLS inspection and IDPS. So don't ask, which one is better? Ask, what problem am I solving? Need scalable outbound NAT? Think NAT Gateway. Need centralized security inspection and policy enforcement? Think Azure Firewall. And in more advanced architectures, these services aren't necessarily interchangeable. The correct design depends on your routing and security requirements. Now we reach one of the most important architecture lessons in this video. Full inspection isn't achieved simply by deploying Azure Firewall. You must deliberately design and validate each traffic path. Start with internet-bound traffic. If workloads must reach the internet through Azure Firewall, configure routing so those connections are steered toward the firewall. Next, examine spoke-to-spoke communication. If traffic between application networks must be inspected, configure the appropriate UDRs, VNet peering, and forwarding behavior so those flows traverse the firewall. Then look at hybrid connectivity. Traffic moving between Azure and on-premises environments through VPN or express route introduces additional considerations: BGP routes, gateway routes, route propagation, asymmetric routing, and return paths. Multi-region environments add another layer of complexity. So don't ask, do we have Azure Firewall? Ask, which path does each important packet actually take? Then validate the answer using effective routes, network watcher, firewall logs, and connection testing. Never assume inspection. Prove the path. Here's the architecture visually. The hub VNet contains shared networking services such as Azure Firewall and, depending on your design, connectivity to on-premises networks through VPN or express route gateways. Your application workloads live in separate spoke VNets connected to the hub through VNet peering. Now look carefully at the arrows. A workload sending internet-bound traffic follows a route that points toward Azure Firewall. The firewall evaluates that traffic against its policy and, when permitted, forwards it toward the destination. For spoke-to-spoke communication, you can configure routing so traffic travels: spoke A, hub firewall, spoke B. For hybrid communication, you must also design the gateway and routing configuration so the forward and return paths remain valid and traffic doesn't unexpectedly bypass your inspection point. This is why hub-spoke security is really a routing architecture. The firewall provides the inspection. The route tables, peerings, gateway configuration, and propagated routes determine whether packets ever reach it. When designing this architecture, draw every important traffic path in both directions. If you can't explain the return path, the design isn't finished. Instead of memorizing that every Azure subnet needs a route table, think in terms of traffic paths. Start with workload subnets. If internet-bound or private traffic must pass through Azure Firewall, configure the required routes so Azure selects the firewall as the next hop. Next, examine spoke-to-spoke communication. Make sure the combination of UDRs and VNet peering sends that traffic through the firewall when inspection is required. Then examine hybrid connectivity. If you're using VPN or ExpressRoute, review gateway routes, BGP learned routes, route propagation, and the return path between Azure and on-premises. Finally, examine multi-region connectivity separately because cross-region routing can introduce additional paths and routing requirements. Don't blindly attach the same route table everywhere. Instead, ask 4 questions. Where does this packet start? Where is it going? Which device should inspect it? And how does the return packet get back? If you can answer all 4, you're designing routing instead of guessing. Traditional hub-spoke architectures give you a lot of control, but managing route tables across dozens or hundreds of networks can become difficult. Azure Virtual WAN provides another approach. With a secured virtual WAN hub and routing intent, you can define routing policies that steer internet traffic, private traffic, or both through a supported security solution such as Azure Firewall. Instead of manually maintaining the same routing logic across large numbers of spokes, Virtual WAN centralizes much of that traffic steering. That's particularly valuable in large environments with multiple regions, branch offices, VPN connections, express route connectivity, and many connected VNets. But don't interpret routing intent as routing no longer matters. It matters more than ever. Virtual WAN is simply managing more of that routing centrally for you. For learning Azure networking, traditional hub-spoke with UDRs is excellent because you can see exactly how packets move. At enterprise scale, Virtual WAN can reduce the operational complexity of managing those paths. Architecture challenge. You deployed Azure Firewall in the hub and configured 0.0.0.0/0 on every workload subnet to point to it. Does that automatically mean every traffic flow in your Azure environment is inspected? No. That route primarily addresses traffic matching the default route. You still need to examine private address routes, spoke-to-spoke communication, hybrid connectivity, propagated routes, peering behavior, and return paths. The lesson is simple. Don't validate firewall architecture by asking, "Did we deploy Azure Firewall?" Ask, "Which route does this packet actually take?" That's the question a network engineer asks. DDoS network protection and web application firewall solve different parts of the attack problem. DDoS network protection helps defend Azure resources against network layer volumetric and protocol attacks. But imagine an attacker sends a perfectly valid HTTPS connection containing a malicious web request. That's an application layer problem. A web application firewall, or WAF, on services such as Azure Application Gateway or Azure Front Door, can inspect HTTP and HTTPS requests and apply rules designed to detect attacks such as SQL injection and cross-site scripting. Think of the layers like this. DDoS protection helps keep the network available. Azure Firewall controls network and application connectivity. UAF protects the web application layer. None of them replaces the others. Together, they create defense in depth. And because Azure capabilities and pricing programs change over time, always check Microsoft's current DDoS and WAF pricing documentation when calculating the financial benefits of combining these services. When an attack ends, your security team will want answers. When did the attack begin? Which resource was targeted? How large was the attack? What traffic patterns were observed? And when did Azure begin mitigation? Start with Azure Monitor and the DDoS metrics available for the protected resource. If you've enabled the appropriate diagnostic settings and sent supported DDoS logs to a log analytics workspace, you can also use Kusto Query Language, KQL, to investigate the event. On screen, I'll show an example KQL workflow using the tables and fields available in our environment. But here's something important. Don't blindly copy a query from another environment. The exact diagnostic categories, table names, and field names available to you depend on your Azure monitoring configuration and the current logging schema. So use this process. Confirm diagnostic settings. Identify the DDoS logs being collected. Open log analytics. Inspect the actual schema. Then build your query around the data that exists. Learning how to investigate telemetry is much more valuable than memorizing one KQL query. Technology isn't the only thing you need during a serious DDoS attack. You also need an incident response process. Eligible DDoS network protection customers can access Microsoft's DDoS Rapid Response, or DRR, team for specialized assistance during an active attack. The team can help with attack investigation, mitigation-related support, and post-attack analysis depending on the situation and your eligibility. But don't wait until an attack begins to figure out how to contact them. Before production goes live, document your escalation process. Know who opens the Microsoft support case. Know who owns network response. Know who communicates with application teams. And know where your DDoS telemetry is being collected. The middle of an attack is the wrong time to create your incident response plan. Let's bring everything together. First, DDoS protection. Use Azure's DDoS capabilities to help protect eligible public-facing Azure resources against large-scale network attacks, and consider DDoS network protection when you need advanced monitoring, adaptive protection, support, and response capabilities. Second, Azure Firewall. Place centralized security controls into the network path when you need network rules, application filtering, threat intelligence, logging, and advanced inspection. Third, routing. This may be the most important lesson of the entire video. Deploying a firewall doesn't mean traffic automatically passes through it. UDRs, VNet peering, BGP, VPN and express route routing, virtual WAN, and return paths determine where packets actually travel. And finally, defense in depth. DDoS protection, Azure Firewall, network security groups, WAF, private connectivity, monitoring, and identity controls each protect different parts of the architecture. Enterprise security isn't one product. It's layers working together. Next up in the Azure Networking Masterclass, we're going deeper into securing access to Azure platform services such as storage and SQL. We'll compare service endpoints with private link and private endpoints. Service endpoints allow supported Azure services to identify traffic originating from authorized virtual networks and subnets. But enabling a service endpoint alone isn't enough. You must also configure the pass resources network access controls to restrict access to the approved VNets or subnets. When those restrictions are correctly configured, network controls can reduce the value of stolen credentials such as a leaked SAS token, because requests originating from unauthorized networks can still be denied. Private endpoints take the model even further by giving supported pass services a private IP address inside your virtual network. Service endpoint or private endpoint? Which should you use? That's what we'll build next. Hit subscribe so you don't miss it. Final checkpoint. A DDoS event just ended, and your manager asks, what was targeted, when did the attack happen, and what does Azure telemetry tell us about the event? Where do you start? First, review Azure Monitor DDoS metrics for the protected resource. Next, check the diagnostic logs you've configured for DDoS protection. If those logs are being sent to Log Analytics, inspect the available tables and fields and use KQL to investigate the event. Don't assume a specific table or field exists until you've confirmed the diagnostic configuration and schema in your environment. That's the final lesson. A production security architecture doesn't just block attacks. It gives you the telemetry to understand what happened afterward. Protection plus visibility. That's real operational security.